Hello everyone, today we are going to talk about question number 6, which is wireless power supply. So basically, wireless power transfer can divide into two groups, which is electromagnetic induction and electromagnetic radiation. But today we are going to talk about electromagnetic induction. In electromagnetic induction, it can divide into inductive coupling and capacitive coupling. So before I introduce to you all the techniques used in wireless power transfer, I would like to talk about this man. He is Michael Faraday. So in Michael Faraday's first experiment, he set up the apparatus as shown in the diagram. Now I would like to explain this experiment to you all. When a switch is switched on, there is electric flow through the wire coil, and there's a magnetic flux leaking and cut the wire coil in a secondary coil. And this causes an electric current to produce. When electric current produced, there's a magnetic field produced and the compass will change direction. So after this experiment, Michael Faraday came into his law, which is electromagnetic induction. So what is electromagnetic induction? It's the effect of producing an induced electromotive force when there is a relation motion between conductor and magnetic field. So this is a basic idea of Michael Faraday's law. He believed that when electrical charge can change into magnetic field can also change to electrical charge. So this science shows reversible. Besides that, he also stated that the magnitude of induced electromotive force is directly proportional to the rate of change of magnetic flux linkage. Michael Faraday comes up with an idea of how to increase magnitude of induced EMF. There's three ways. The first way is increase the speed of relative movement, and the second way is increase the number of turns per unit length, and the third way is strength of permanent magnet. So how wireless power supply works? The first method is inductive coupling. The main idea of this technique is induced coupling between coil wire and magnetic field. So in this technique, it consists of transmitter and receiver. So when an AC current is passed through the conductor, which is a transmitter, magnetic field is produced around it. This causes leakage of magnetic flux and changing of magnetic field. When a second conductor approaches, the cutting of magnetic flux produces an induced EMF in the receiver, and the induced EMF has same frequency as current of the AC electrical supply in transmitter. This causes the electric current to flow through. As you can see, this is wireless power transfer. So now I want to introduce to you all that is capacitive coupling. Capacitive coupling is a transfer of alternating electrical signals or energy from one segment of a circuit to the other using a capacitor. The coupling provides a medium for the AC signal while blocking the DC energy. So this is a capacitor, and this is a symbol of capacitor. A capacitor is able to block low frequencies such as DC and pass high frequencies such as AC because it is a reactive device. It responds to different frequencies in different ways. To low frequency signals, it has a very high impedance or resistance, so low frequency signals are blocked from going through. To high frequency signals, it has a low impedance or resistance, so high frequency signals are passed through easily. Coupling wireless power transmission system is characterized by its two sets of asymmetric dipoles consisting of active and passive electrodes positioned on the power transmitting and receiving sides. Power is transmitting using an induction field generated by coupling these two sets of asymmetric dipoles. If we connect an AC voltage across the two conductors, an AC current will flow as the electrons are alternately attracted or repelled by the voltage on the opposite plate. There's a complete AC circuit even though there is no hardwire circuit connection. The electrical field inside the capacitor between the two plates is what completes the AC circuit. This configuration achieves a high efficiency wireless power transmission with high positioning flexibility. So this is a basic idea of capacitive coupling.
Each type of wireless power transfers have their own advantages and disadvantages and would be useful under different circumstances because of it. First, we have electromagnetic induction. It has a greater spatial freedom than capacitive coupling, which means there is no need to precisely align the source and object. It will still work even if it's not directly in contact with the source. Induction is more versatile too, as it can convert any source of sufficient mechanical energy into electrical energy. The range of induction is slightly bigger than capacitive but smaller than without resonance. The primary and secondary coil have to be kept in close proximity. If long-distance induction was to be achieved, a very big magnetic field has to be produced, and the number of coils required would be expensive, inefficient, and impractical. Very little power would be received regardless. There is also the more compact and lighter capacitive coupling. It is more convenient and portable. It has low cost as resistors and capacitors are relatively cheap. Since it has low electromagnetic radiation and no significant amount of heat generated, it is safer to place near batteries. However, all of these come with many disadvantages. Capacitive coupling is only applicable to small gaps due to constraints on the developed voltage. It has much less vertical freedom and will only likely to work if the object is in direct contact with the source, although you can place it anywhere horizontally on the source. High voltages on the electrode is a safety hazard. The energy can transfer via conduction and harm the user. Since this method also degrades and distorts the low frequency performance, it needs high capacitance ratings to work.
I'll be talking about application of wireless power transmission. Wireless power transmission is the transfer of electric energy from a power source to an electric load without interconnecting main conductor. Wireless power transmission is useful in cases where the interconnecting wires are inconvenient, hazardous, or impossible. Electric current is passed through a coil of copper wire, and the coil will produce a short-range magnetic field. When a second coil of copper wire is placed within the field, electric current will flow through it. The magnetic field has transferred the electrical power from one coil to the other. This principle is called induction. What are the applications of wireless power transfer? Wireless power transfer can eliminate traditional charging system in place today. Instead of plugging in mobile phone or laptop via power cord to charge battery, wireless power can be harnessed and implemented in a home such that a laptop and phone can charge continuously and wirelessly without the need of plugging in anything. Handphone and laptop. Energy is sent through an inductive coupling to an electrical device, which can then use that energy to charge batteries or run the device. Induction chargers use an induction coil to create an alternating electromagnetic field from within a charging base, and a second induction coil in a portable device takes power from the electromagnetic field and converts it back into electric current to charge the battery. Wireless power transmission generates electricity by taking magnetic flux and moving it through the coil to create electricity. Power from the socket is alternating current, which changes direction 60 times a second. Electrons are moving back and forth, and that is the key to wireless charging. Two induction coils in proximity combine to form an electrical transformer. Greater distances between sender and receiver coil can be achieved when the inductive charging system uses resonant inductive coupling. Have you ever wondered how an electric toothbrush charger works? Inside the toothbrush is another coil going outside the protuberance under the plastic, going round and round, then connecting to the toothbrush itself. a changing magnetic field going near a conductor, the field will induce a current in that conductor. It is actually how a transformer works. The current inside the first coil makes a changing magnetic field, and that makes a current flow inside the second coil without having to touch it. That charges the toothbrush itself. Inductive charging uses electromagnetic field to transfer energy from transmitter to receiver. To enhance the inductive power transmission, we use resonance. Resonance is a phenomenon when maximum amplitude in the system produced when frequency by the external force equals to the natural frequency of the system. At resonant frequencies, small periodic driving forces have the ability to produce large amplitude and oscillation due to the storage of vibrational energy. Another way to enhance inductive power transmission is by resonant inductive coupling. Resonant inductive coupling consists of one drive coil in the primary side and one resonance circuit on the secondary side. It is based on Faraday's law of electromagnetic induction. It makes use of coils. The coils are not connected through wire or any other kind of materials. Transfer of energy is due to mutual induction. It's based on the concept that an oscillating electric field produces magnetic field and an oscillating magnetic field produces oscillating electric field. The approach of second coil, which also has the same resonant frequency as the source, will couple resonating anywhere within that region and converts oscillating magnetic field into electric current within second coil. This causes a larger electric current.
Both inductive and capacitive can be extended by resonance. Resonance has very little need to have the source and object precisely aligned and would be able to charge multiple devices. Combining this with the extended range resonance provides, using resonance for wireless power transfers would be more convenient for the user. The cost of maintenance is also less than induction, since there is no direct connectors. However, it is difficult to identify and tune the source and receiver to have the same resonant frequency, making resonance harder to produce. The power transfer is also less efficient due to high energy loss.